Hi everyone, welcome to our third and last video on section 11.5. We're going to be talking about finding the intersection points of polar curves. Now that we know how to graph polar equations, we're going to take a look at multiple polar equations at the same time. So for instance, this picture of the cardioid and the circle is going to be typical of what we'll look at in this video. We've got graphs of two polar equations and we want to find out where they intersect. And we'll take a look at some algebraic ways to do that. The other thing we want to do is we want to be able to describe polar regions in set builder notation. So the reason why we want to do that is when you get to calculus 2, you're going to want to be able to find the areas of regions in 2 dimensions that are described by polar curves. So a typical calculus 2 problem might be to find the area that is inside the green circle but outside the purple cardioid. So the region in question, inside the circle but outside the cardioid, would look like this. You would have that crescent shape there that I've shaded in blue. And in order to find that area, I would have to be able to describe it in a little bit more detail than what I've done here, right? What we're going to need to do is be able to say what does it mean mathematically to be within this region so that we can define it and then find its area. So without further ado, let's take a look at some examples. Alright, just above example 4 from the guided notes, we've got some guidelines for finding points of intersection of graphs of polar equations. This box is taken from page 953 of your book. So the first bullet point there is going to be the first step there. Step 1, we want to sketch the graphs of the two polar curves that we want to see the intersection points for. Now, once we've graphed the points, we want to check to see if the curves intersect at the pole. And we'll explain why we do that in step 1 with the first example. Now, step 2, we actually do a little bit of algebra, a little bit of trigonometry. Solve for the pairs r theta, which satisfy both polar equations. Now, if we're lucky, that's the end of the story. Polar coordinates and equations with polar coordinates can be kind of wild sometimes. So there's a couple other bullet points there. They probably don't make sense right now. They're written a little bit abstractly. But we'll do at least one example where we have to do a little bit extra work. So you'll see in particular the fourth bullet point in action. If you'd like to see more examples, you could take a look in your textbook. That's definitely a good source for examples other than the guided notes. So without further ado, let's get into example 4. Find the polar coordinates of the points of intersection of the graphs of r equals 3 cosine theta and r equals 1 plus cosine theta. Now, for this sort of problem, I don't expect you to graph these by hand. What I want you to do is use your graphing calculator. So I'm going to put my TI-83 right here so we can see it. And I'm going to hit my mode key. First of all, make sure I'm in polar mode. So that's line 4 here. If you're using a TI-83 or TI-84 similar to mine, you're going to want to make sure POL is highlighted. If it's not, hover over it with the cursor and hit enter. Once you've done that, hit your Y equals button. You should have some space to input some polar equations. So we've got r equals 3 cosine theta. I'm going to type that in. And we've got r equals 1 plus cosine theta. So I'm going to type that in as well. Now I'm going to plot this and see what I get. I'm probably going to have to adjust my viewing window some. So it looks like I've got a circle. And looks like probably a cardioid. We might want to zoom in a bit just to get a better picture. If you remember from the last video, we should recognize 3 cosine theta is a circle, 1 plus cosine theta is a cardioid. So let's zoom in just a bit to see this in a little bit better detail. So my x is zoomed out pretty far. Let's look from, say, -4 to 4 on the x, -4 to 4 on the y. I'm just picking numbers here. Look like reducing my width by about half would be a good idea. So now it's a little bit easier to see the heart shape of that cardioid. And if you really want to see that this really is a circle, remember that looks a little bit oval shaped because my viewing window is a rectangle, not a square. I can hit zoom 5 to correct for that. That's going to give me a nice square viewing window. It's going to make circles look like circles. So yeah, 3 cosine theta is definitely a circle. Now the only downside is that zoomed out for me a little bit on the x-axis, but we can still see that that's a cardioid. Alright, so as a cardioid, let me remind us that we want to check to see if the curves intersect at the origin and they intersect at the pole. And yeah, they do. The circle hits the origin and the cardioid hits the origin at that point of the heart. So if I want to zoom in and see that without losing my square, I can hit zoom 2. So that's zoom in, and then my origin is selected. I hit enter on that. And that's going to zoom me really far in. I mean, it's going to obscure most of the shape of the graph, but if you're not sure whether or not you intersect at the pole, you can definitely do that. And you can see the cardioid coming around and just touches the circle right at the pole. So the pole is an intersection point. Okay. Now, the reason we want to find that in step 1 instead of step 2 is because the pole can be represented in any number of ways. As long as r equals 0, any value of theta will give me the pole. So it might very well be that r is 0 for one value of theta here, r is 0 for another value of theta there, and you're not going to be able to find that really easily algebraically. So what we want to do is do this in step 1, make sure, well, verify whether or not the graphs intersect at the pole. So, that in mind, they intersect at the pole. That's one point at which they intersect. So, let's do a little bit of algebra here and find the other intersection points. If I zoom back out, we should be able to estimate the number of intersection points that we have. And if you remember what the picture looked like before, we should have 2 other intersection points. We'll see that again as the cardioid populates on screen. So it looks like we've got one intersection point there in the first quadrant, hits the origin, and then one more intersection point in the fourth quadrant. So it looks like we've got 3 intersection points in all. We've got the pole and then 2 others. So we can find those algebraically. So what I'm going to do is set equation 1 equal to equation 2. I'm going to set 3 cosine theta equal to 1 plus cosine theta. And this corresponds to bullet point number 2. So we're trying to solve for pairs that satisfy both the first and the second equations here. So if I manipulate this around, swing the cosine theta over, and divide both sides by 2, I'm going to get cosine theta equals 1/2. And if I remember, all students take calculus, that'll give me cosine is positive in the first quadrant and the fourth quadrant, so that's what we expected. We saw intersection points in quadrants 1 and 4. And let's see, so what angles have a cosine of 1/2? If I remember my reference triangles here, so if I look in quadrant 1 real quick and just remind myself, maybe I've forgotten which angle this is. This looks like a 30, 60, 90 reference triangle. So the angle opposite the root 3 is going to be a 60-degree angle, or pi over 3 radians. So we're going to get theta equals pi over 3, or theta equals 5 pi over 3. Okay. So that's a good sign. That gives us two solutions. We expected 2 intersection points. And in order to figure out the r coordinate, so I want the polar coordinates of the points of intersection, so I need both coordinates for both points. I've got the theta coordinate. Now I need to find the r coordinate, and shouldn't matter which equation you use to plug in your theta value. I'm going to use r equals 1 plus cosine theta. So if I plug in pi over 3 here, I've already got a nice reference triangle written out. Cosine of that angle is 1/2. What do you know? That's the way we designed it. So r is going to be 3 over 2. And if you do the same thing in the fourth quadrant, 1 plus cosine of 5 pi over 3, well, again, by design, or you can draw the reference triangle out, cosine of 5 pi over 3 is going to be 1/2. So again, we're going to get an r value of 3/2. So we've got the pole as a point of intersection. Then we've got the point 3/2 comma pi over 3, right, because we plugged in pi over 3 and obtained an r value of 3/2. And then when we plugged in 5 pi over 3 for our angle, we obtained an r value of 3/2 again. So we've got our 3 points of intersection: the pole, 3/2 comma pi over 3, and 3/2 comma 5 pi over 3. So I can box these off. And let's see if we want to check our answer. If you want to go hardcore and do it without the calculator, you should plug in pi over 3 and 5 pi over 3 on the left-hand side. Make sure you get 3/2 for r again. You can always check with your calculator as well. So if I hit my trace button, it's going to allow me to input an angle. So if I type in pi over 3, so it's looking at my first equation. Notice my x-coordinate is 0.75, my y-coordinate is 1.299, so almost 1.3 there. And if I go to my second equation, r equals 1 plus cosine theta, you should see, if we plug in pi over 3 again for theta, that we get the same thing. So 0.75 and then that 1.299 number. Now it might be that you're off by maybe the 8th decimal point. If that's the case, don't worry about it. But if you're off by like the 3rd or 4th decimal place, then you might want to check your answer. Then we can go back again. And yeah, we can see we get that same 0381 ending to that number. Now, notice that when I set these two expressions equal to each other, we did not get the pole as an intersection point. So let's think about why that is. Well, if r equals 0 here in the first equation, we're going to have an angle whose cosine is 0, right? If r equals 3 cosine theta, this is going to hit the pole when r equals 0. So this means that cosine theta has got to be 0. And cosine theta is going to be 0 when your x-coordinate is 0, so at pi over 2 and 3 pi over 2. On the other hand, this equation, we will be at the pole when 1 plus cosine theta is 0, or if you think about it with cosine theta by itself, cosine theta is -1. And that's going to happen when x is -1. If you think about the unit circle, that's going to happen when theta equals pi. So it's true that both of these polar curves hit the pole, but they do so for different values of theta. So that's why setting the expressions equal to each other doesn't allow us to pull out the pole as a solution. So, this was an easy example. We got away with finding all 3 points using just the first 2 bullet points. We'll take a look at another example like that. I'm going to look at part C. So part C, we've got r equals 9 times cosine of theta and r equals sine theta. So our step 1, just like before, I'm going to graph these out. So 9 cosine theta and sine theta. And if I hit graph, I'm probably going to find that I need to zoom out. Yeah, because 9 cosine theta is going to be big circle of diameter 9, like we saw last time. And then sine theta is going to be that little tiny circle we see there of diameter 1. Now the benefit of being zoomed in this super close is that we see that the pole is going to be an intersection point, right? The cosine circle is going to hit the pole at its leftmost point. Sine circle is going to hit the pole at its bottommost point. All right, so r equals sine theta, right? If theta equals 0, your r would be 0. On the other hand, if theta equals, say, pi over 2, cosine of pi over 2 is 0. So again, you have 2 curves that are going to hit the pole at 2 different angles. So the pole is an intersection point. So I'm just going to make a note of that on the left so we don't forget. Now if I zoom out, really I don't even need to zoom out to see the intersection points because the sine circle is so small. It looks like we've got 1 additional intersection point, and it's going to be in the first quadrant. So if I zoom out, just so you can see the full sine circle, say negative 9 to 9, and let's say negative 5.5 to 5.5. That should allow us to keep roughly the square shape. So there's my 2 circles. And step 2 is going to be to set the 2 expressions for r equal to each other. So 9 cosine theta equals sine of theta. So we've got an equation with both sine and cosine in it. So we've seen this sort of thing before. We've seen that it's beneficial to divide both sides by cosine theta. Normally we want to avoid dividing both sides by something with a variable in it, but cosine of theta and sine of theta cannot both be 0 at the same time. So that's an explanation that we've seen before. So if you've got cosine theta and sine theta in the same equation, you can divide both sides by cosine theta, get your factor of tangent. And tangent theta equals 9. So if I sketch that out in the first quadrant, this is not to scale, but what I'm going to get is a really tall triangle. Base length is 1, the height's going to be 9, right? Tangent's opposite over adjacent, so that's how I made my drawing. And that means my hypotenuse, if I use the Pythagorean theorem, hypotenuse is going to be square root of 1 squared plus 9 squared. So the hypotenuse is going to be root 82. And I show you this to show you that this is certainly not one of our reference triangles, right? So remember what we do when we have something that's not a reference triangle. I've got to use my inverse trigonometric functions here. So I'm going to write down theta is the arctangent of 9. Now, that's half the battle. We found theta. Remember, when you're asked for a point, points have 2 coordinates, right? If I'm talking about rectangular coordinates and I ask for a point, I need x comma y. If I'm looking at polar coordinates and I ask for a point, I'm looking for r comma theta. So here's theta. I'm asking for the point of intersection, so I also need r. So I'm not finished quite yet. I need to go back to one of these equations, and I need to plug in that theta value. So I'm going to choose the sine equation. So sine of the arctangent of 9. So here's my arctangent of 9. What's the sine of this angle? The sine of this angle is going to be opposite over hypotenuse. So I'm going to get 9 over radical 82. I don't require you to rationalize your denominator, but you can also write this as 9 radical 82 over 82. So that's going to give me my point in the first quadrant. So my point in polar coordinates, my point of intersection is going to be 9 radical 82 over 82, comma, theta, which is arctangent of 9. So our answer here is that these 2 polar curves intersect at the pole and at the point 9 radical 82 over 82, comma, arctan of 9. So if we can do problems A and C, problems B, D, and E in this set of guided notes are pretty similar. So what I'm going to do is look at one example that's outside the guided notes, and we're going to find the intersection points of the polar curves r equals 3 and r equals 6 cosine of 2 theta. So let's take a look at the graph of these 2 equations. So I'm going to hit my y equals key. I'm going to type in r equals 3 and r equals 6 cosine of 2 theta. And take a look at the graph. So we've got the circle and the rows, so we would expect the equation r equals 3 to be the circle, radius 3 centered at the pole, and r equals 6 cosine 2 theta. We should recognize that as having the form of the rose curve that we talked about in the second video. So observe that there are 8 intersection points on the graph. They don't appear to intersect at the pole, right? Circle of radius 3 doesn't hit the pole, right? So the 2 curves won't intersect at the pole, but they will intersect 8 other times. So let's try what we've done in the last couple of problems and set 2 expressions equal to each other. So 6 cosine of 2 theta equals 3. So we get the cosine of 2 theta equals a half. And this is one of those problems we did back in chapter 10 where we say, okay, let u be 2 theta. So then we're solving cosine of u equals a half. So that tells me that u, there's 2 possible solutions for u. Since cosine's positive, we're in the first or the fourth quadrant. And I'll leave it to you as an exercise to show that what we would get is pi over 3 plus 2 pi k. And the fourth quadrant solution would be 5 pi over 3 plus 2 pi k. So that's going to tell me, well, this is u, this is 2 theta. So if I remember that, 2 theta is pi over 3 plus 2 pi k. 2 theta is 5 pi over 3 plus 2 pi k. I'm going to divide both sides there by 2. And what we're going to get is theta equals pi over 6 plus pi k. And theta equals 5 pi over 6 plus pi k. And of course, k is an integer. So if theta equals pi over 6, then if I plug that into my equation here, I should get 6 times cosine of pi over 3. Well, if I write that down, when theta equals pi over 6, r equals 6 cosine of 2 times pi over 6. So 6 cosine of pi over 3, well, cosine of pi over 3 is a half. So I get r equals 3. And I notice in hindsight that I could have just looked at the other equation and said, oh, well, no matter what theta is, anytime I have an intersection point, it's going to happen at r equals 3. Okay? So that tells me that I can write down r comma theta equals 3 comma pi over 6. This is one intersection point. And likewise, if you go through the same exercise with the second equation and k equals 0, you get 3 comma 5 pi over 6. There's another intersection point. Now if we continue, when k equals 1 here, when k equals 1, we get pi over 6 plus pi. So when k equals 1, we get pi over 6 plus pi equals 7 pi over 6. 5 pi over 6 plus pi is going to be 11 pi over 6. Right, because pi is just 6 pi over 6, so get your common denominators and add the fractions. So I'm going to get 2 more intersection points here. So these are my angles theta. And I know that if I look at my first equation, r equals 3, that's going to happen for any intersection point. So I'm going to get 3 comma 7 pi over 6 and 3 comma 11 pi over 6. And of course you can always plug 7 pi over 6 and 11 pi over 6 in here, and you should get the same thing. You should get r equals 3. Now, if I look at k equals 2, that's going to take me outside the scope of 0, 2 pi, and what you'll find when k equals 2, you're going to get pi over 6 plus 2 pi, you're going to get 13 pi over 6. And likewise, 5 pi over 6 plus 2 pi is going to be 17 pi over 6. These are actually going to give you repeats, right? Because 13 pi over 6 minus 2 pi is pi over 6, so you have coterminal angles here. Likewise, 17 pi over 6 is coterminal with 5 pi over 6. So you're going to get the same points again. So what this method has done for us is it's generated 4 solutions, which sounds like a lot, but remember our graph showed 8 intersection points. But that begs the question, well, how do we get the other 4 points? And why didn't we get the 4 points, the other 4 points, when we solved the equation this way? Well, remember in polar coordinates that any point can be represented infinitely many different ways. So in particular, if I look at the circle r equals 3, r equals 3 is going to give the same graph as r equals negative 3. Right, these are the set of points that are 3 units away from the pole in any direction. And these are also the same set of points. This is also the set of points that are 3 units away from the pole in any direction. It's just our perspective is a little bit different here. So if I look at this circle in polar coordinates, I might have, say, the point 3 comma pi over 6, right? But this is also the same point as negative 3 comma 7 pi over 6. 7 pi over 6 would be the angle in the third quadrant in the opposite direction. So this sort of thing is the source of one of the guidelines that we talked about for finding the points of intersection of polar equations. So this fourth bullet point here is what I want to direct our attention to. So if we substitute negative r for r, so that is we change the radius to its negative, and consider that we're looking in the opposite direction. That's what this is saying here. So theta plus some odd multiple of pi is going to point you in the opposite direction. So opposite radius, opposite direction. That's the source of this fourth bullet point here. So what this is going to boil down to for us is if I look at the equation of the circle, I can substitute negative r for r, and what I'll get from that is the equation negative r equals 3, or simply r equals negative 3. So what we're going to do is we're going to repeat step 2. We're going to repeat the process of setting the expressions equal to each other. But we're going to do that looking at the circle in a different way here. So if I consider r equals, I want to look at r equals negative 3 this time, and r equals 6 cosine of 2 theta. So I get 6 times cosine of theta, cosine of 2 theta equals negative 3. So cosine of 2 theta is negative 1/2 this time. What that's going to give me, if I look at cosine of u equals negative 1/2, that's going to give me u equals 2 pi over 3 plus 2 pi k, and u equals 4 pi over 3 plus 2 pi k. So if we go through the same set of steps that we did last time, what we're going to get is theta equals pi over 3 plus pi k, and 2 pi over 3 plus pi k. So to make a long story short here, we're going to end up with theta equals pi over 3, 2 pi over 3. So we'll get that when k equals 0. And then when k equals 1, we get 4 pi over 3 and 5 pi over 3. So we get these points, these angles when k equals 0. We get these angles when k equals 1. So r equals negative 3. I'm going to get the points negative 3 comma pi over 3. I'm going to get negative 3 comma 2 pi over 3. And so on for the other angles, 4 pi over 3 and 5 pi over 3. And I can clean up the r coordinates here by remembering that if I look at negative 3 comma pi over 3, for instance, and here's pi over 3. And what's in the opposite direction of that? Opposite direction of that, if I add pi, so pi over 3 plus pi, it's going to give me 4 pi over 3. So negative 3 comma pi over 3 is going to be 3 comma 4 pi over 3. And I get 3 comma 5 pi over 3 similarly. This, if I consider 4 pi over 3, I can subtract pi to get the opposite angle. 3 comma pi over 3 and 3 comma 2 pi over 3. So this is how we get the other 4 intersection points. We have to change our point of view, and we have to think of the circle r equals 3 as r equals negative 3. This is one of the things I was talking about before, about how finding the intersections of polar curves can be a little bit wild, and it all goes back to the fact that polar points have infinitely many representations. So there's 4 of our solutions, and then the other 4 solutions, we had 3 comma pi over 6, and then 3 comma 5 pi over 6, 3 comma 7 pi over 6, 3 comma 11 pi over 6. Now, your book doesn't do any examples like this, but there are some problems in this section where you have to use set builder notation to describe the regions that are determined by polar curves. Now, this is going to be useful for you in Calculus 2 when you want to find the areas of regions determined by polar curves. What you're going to need to do is you're going to need to be able to express what those regions are in a precise way so that you can find their areas. So start with a relatively simple example. We want to use set builder notation to describe the region inside the circle r equals 5. So if I think about what this circle looks like, circle centered at the origin, centered at the pole, radius 5. Now, if I think about the region inside my circle, so all these points in red here that I'm plotting out, these are all points inside my circle. And what's the characteristic of points that are inside my circle? Well, if I remember what r equals 5 means, r, remember, is the distance from the pole. So the circle, the black circle, is the set of all points that are 5 units away from the pole. If I'm inside the circle, that means I'm closer to the pole than the circle. If I'm outside the circle means that I'm farther away from the pole, right? More than 5 units away from the pole. So that's the key thing to look at when we're talking about points inside the circle. We're looking at points that are closer than 5 units from the pole. So what does it mean to be closer than 5 units from the pole? Well, that's going to mean that the distance from the pole is going to be between 0 and 5, like so. We could possibly be at the pole, but if I'm talking about strictly closer than 5 units from the pole, we have to exclude 5. So we're looking at those points. Now, when we express this in set builder notation, we're always going to start these the same way. I'm going to start with a brace, or some people call this a curly bracket. I'm going to look at the set of all points r comma theta, and then I'm going to add some qualifiers. Now, my first qualifier is this one. I'm going to say that 0 less than or equal to r is less than 5, or more casually, you might say r is between 0 and 5, including 0, not including 5. Now, that tells me what r can be. Now, at first, we might think there isn't really a restriction on theta, and there really isn't from a set perspective. But when we're thinking about Calculus 2 applications, it's going to be important that if I want to find the area inside the circle, that I'm only counting each part of my circle one time. So as I'm looking at my first quadrant, and I'm thinking about angles between 0 and pi over 2, I don't want to retrace that every time I think about coterminal angles. So what I'm going to do is I'm going to restrict my attention to the interval 0, 2 pi. And what that's going to do is that's going to trace out my circle exactly one time, nice and neat. Now, the only other thing that I didn't explain 100% fully is why do we want to say that r is greater than or equal to 0? Why do we say 0 is less than or equal to r? Well, remember that r doesn't have to be positive when we're talking about polar coordinates. So let's say that I didn't do this. Let's say I just said r is less than 5. Let's say I didn't have this 0 less than or equal to in here. Well, if r is less than 5, I could potentially have a point like -7 comma pi. -7 is less than 5. Pi is between 0 and 2 pi, so this would technically be in my set. But -7 pi would be outside my circle here. -7 pi, remember, would be 7 units in the opposite of the pi direction. So I want to exclude points like that. So that's why I need to make sure I say that 0 is less than or equal to r here. Okay, so let's move on to part B, where we want to look at the same circle. So we want to look inside the circle r equals 5 and just in quadrant 2. So I'm looking at points that are in quadrant 2 and see if we can compare contrast a little bit here. Pause the video and think about what needs to change here in order to give me just this region. So if you pause the video there, compare your answer to mine. So I got the set of all points r comma theta, where r is between 0 and 5, including 0, not including 5, and pi over 2 less than theta less than pi. That's going to restrict my attention to the second quadrant where I get all those points exactly one time. Now, one thing I'll note here is when I say in quadrant 2, I excluded the quadrantal angles here because the quadrantal angles are not technically in quadrant 2. But from a calculus 2 perspective, when you're trying to find the areas of polar curves, the endpoints of your region in question don't matter. So if you look at similar problems in your book and you look at the answers in the back, I think they do this same problem just in quadrant 3. They actually do include the endpoints. And again, that's probably because from a calculus 2 perspective, it doesn't matter if you include the endpoints or not when you're talking about area. But from a pre-calculus perspective, if we want to be 100% rigorous and 100% correct, we would have to exclude pi over 2 and pi. So with that, let's take a look at one last example that's a little bit more complicated. Here I want to use set builder notation to describe the region inside the circle r equals 3 cosine theta, but outside the cardioid r equals 1 plus cosine theta. So I'm going to graph that and remind us what these look like. I say remind because these are actually the same curves that we looked at earlier. So we've got r equals 3 cosine theta and 1 plus cosine theta. So we looked at these in example A. We actually found the intersection points of these two curves. So if I use a viewing window, let me go ahead and use -3 to 3 on the x, -2 to 2 on the y. And I'll hit zoom 5 right away just to square that off. So we've got that circle of diameter 3. It opens to the right, and then the cardioid. So now that we've got this little reminder sketch, what I'll do is I'll draw a sketch here so I can actually draw on it. So I've got my circle, and then I'm going to try and sketch this cardioid as best I can. Got something that looks like this. And if we recall what those intersection points were, those intersection points were 3/2 pi over 3 and 3/2 negative pi over 3. Now the region we're interested in, we want to be inside the circle but outside the cardioid. So we're outside the cardioid, we're farther away from the pole than the cardioid, but we're inside the circle. So we're looking at that crescent-shaped region. So inside the circle but outside the cardioid means we're closer to the pole than the circle, but we're farther away from the pole than the cardioid is. So what I would have to do is I would have to say, well, as always, I start r comma theta, and I'm going to say, well, if I want to be farther from the pole than the cardioid, then that means that 1 plus cosine theta is going to be less than my r value, right? Then I want to be closer to the pole than my circle. So my r value, my distance from the pole, is going to be somewhere between the cardioid and the circle. And if we think about it that way, that's exactly the region that we shaded. So that takes care of r. Now I want to think about theta, and that's why I labeled my intersection points here, because my intersection points are going to tell me where to stop. So if I look past my intersection points, for values of theta out here, notice I don't have anything. But for values of theta in here, for values of theta between my two intersection points, I do have points in this crescent-shaped region. So what I'm going to do is I'm going to say theta is going to be between negative pi over 3 and pi over 3. So I'm going to write negative pi over 3 less than theta less than pi over 3. Now, like I said with the last example, you may see less than or equal to in your book for some of these. So if you say less than or equal to versus less than on an exam, I'm not going to ding you for it. Like I said, the applications to this in Calculus 2, when you're talking about areas, it's not going to affect your answer. So this is the set of all points that are inside the circle but outside the cardioid. I hope those examples were helpful for you. Let me know if you have any questions as you're going over the homework. And next time we'll take a look at section 11.7. We'll continue looking at polar coordinates, but we're going to use them to analyze something you saw in college algebra, which is complex numbers. So we'll look at how complex numbers can be identified by polar coordinates. Till then, see you next time.